Good evening, everyone. Myself, the U. Mahendra Kumar, pursuing BTech in VVIT University, bearing roll number 24BQ1804H6. Today, tell about the seminar topic is Understanding Random Process, Navigation the Dynamic of Uncertainty. What exactly is a random process? A random or stochastic process represents a collection of random variables, each indexed by a specific point in a time. Unlike a single random variable that captures uncertainty at one moment, a random process models how this internet randomness unfolds and evolves through time. Consider the daily fluctuations of a stock price, where each day presents a new uncertainty value, yet these values are part of a large evolving system. Similarly, they have unpredictable interference noise encountered in a communication channel service as another prime example, illustrating how random processes are fundamental to understanding dynamic uncertain systems. Random process versus random variable. A critical distinction. Random variable. A random variable quantifies a single uncertainty outcomes at a fixed point in the time. It provides a snapshot of randomnesses, like outcome of a single coin toss or head toss, or the temperature at noon in a specific day. Random process. In contrast, a random process is an entire family of random variable where each variable corresponds to a different time point. It more akin to a random function or a trajectory of the uncertainty, mapping how probabilistic outcomes manifest over an extended period rather than just a single numeric value. Discrete time, the time indexing, discrete and continuous perspectives. Discrete time process. These processes are indexed by integers, meaning observations occur at distant countable intervals. Example include the daily closing stock price or the number of websites visit each hour. Analysis often involves in difference equations. Continuous time process. In this process, the index can be any real number, allowing for observations at any instant in a given interval. Think of the continuous flow of current in an electric circuit or the precious voltage noise over time. Differential equations are often employed for analysis. Understanding this distinction is a paramount, as profoundly influence the mathematical tools and analytic approaches applied across various applications. Key properties: stationary and independence. Stationary. A process is a stationary if the statistical properties such as mean and variance remain constant over time. This implies that the underlying data generating mechanism does not change. Strict stationary denotes the joint probability distribution of the process is invariant to any time shift. Weak stationary. A more commonly used concept requires only a constant mean, constant variance, and auto covariance that depends softly on the time difference, not the absolute time. Independence. This property describes whether future states of the process are influenced by the past states. As process exhibit independence is the future values are not predicted by the past. Conversely, in a Markov process, the future state depends only on the current state. Completely forgotten is the entire history. Important examples of random process. First one, Bernoulli's process. Bernoulli's process is a sequence of independent trials, each with two possible outcomes. Example, success or failure, heads or tails. With a constant probability of the success, it fundamental for understanding binary events. Poisson process model the number of discrete events occurring with a fixed interval of time or space, such as a customer arrivals at a service desk or radioactive decays. Events happen independently and at a constant average rate. A Markov process characteristics by the Memorial's property, where the future state of the system depends only on its present state, not on the sequence event preceded it. Widely used in modeling sequential decision marking. Moments and correlations. Describing random process behavior. mean function. This quantifies the expected value of the random process at each specific point in the time. It offers insight into the process of central tendency as it evolves. Autocovariance function measure the linear relationship and dependency between two values of the same process at a different points in a time. It indicates how much the value cover with each other. Autocorrelation function, a normalized version of autocovariance that measure the strength and direction of a linear relationship between observation at a time lags. It provides a scale free assignment of the temporal dependency ranging from -1 to 1. These crucial functions collectively enable to us to the characteristics the interacted behavior and underlying dynamics of random process over time, facilitating deeper understanding and prediction. The temperature depends ranging from -1 to 1. This often dynamics of the random process over time, facilitating the values coverage with others. Diverse applications across fields. Telecommunications is crucial for modeling and mitigation noise in communication channels, ensuring reliable signal transmissions and reception. Finance used extensive for modeling stock prices, option pricing, and assigning financial risk in volatile markets. Physics explain phenomena like Brownian motion, describe the erratic moment of particles suspended in a flood. Queuing therapy helps optimize systems by modeling customer allowance, waiting times, and service process is called centers or retail. Simultaneous and analysis tools to effectively study and apply random process. A variety of powerful tools are utilized. Computational software platforms such as MATLAB and Python with libraries like NumPy, SciPy, and state models are indispensable for simultaneous complex random process and performing stochastic analysis. Statistical estimation methods techniques like maximum likelihood estimation (MLE), full form of maximum likelihood estimation, and Bayesian estimation are employed to infer parameters of a random process from observed data, allowing for accurate model fitting and prediction. Predictive modeling through simultaneous and engineering or scientifics can forecast the behavior of the systems under various conditions. Design and robot systems that tolerate uncertainty and optimize performance in the face of randomness. The simultaneous analysis tools are they have three types of softwares. First one, computational software and statistical estimation methods like maximum likelihood estimation (MLE), data allowing accurate model fitting and prediction. Third one, predictive modeling. Predictive model has simultaneous engineers and scientists are forecast behavior of the system under various conditions. Design robust system that tolerate uncertainty, performance in the face of randomness. Thank you. In a random process decades, the simultaneity is equal to device applications of across field telecommunications, crucial for modeling and mitigation noises in the communication channels, ensuring reliable signals transmissions reception. Second one, finance used to extensively for modeling stock prices, option pricing, and pricing assuring a financial risk in the volatile markets. In the volatile market, physics can explain the phenomena like Brownian motions, describe the erratic motions of the particles suspended in a floods and queuing therapy. Queuing therapy helps to the optimize systems by modeling customers' arrivals, waiting times, and service process in call centers or retail. In retail communication systems are effectively study and apply random process. A variety powerful tools are utilized in modeling, simultaneous engineering, and scientifics of the performance in the face of randomness. Techniques like maximum likelihood and estimation are applied to the informed parameters of the random process from observed data, allowing the model fitting and prediction. In fitting and prediction, simultaneous and analysis tools are for three types of the computation statistical estimation methods are MLE of predictive modeling through the simultaneous engineers and scientifics are can forecast the behavior of the system under various conditions. Design robust system that tolerate uncertainty and optimize the performance in the face of randomness. In analysis tools of the Applications are effectively study and apply random process of a variety of powerful tools are utilized in MATLAB or Python. MATLAB and Python used in analysis tools and effectively understanding the navigations employed to the parameters of the random process from observed data, allowing for accurate model fitting and prediction. Predictive modeling through simultaneous engineering and scientists can forecast the behavior of the system under various conditions, design robust systems that tolerate uncertainty and optimize performance in the face of randomness. Thank you.